So here it's just a table, and I've highlighted a couple of entries. Let's first take a look at S equal 2 here. So let's suppose we were doing fitting a line, or if we're doing a transformation, that's a similarity transform where you take two pairs. Notice that if my percentage of outliers is 50%, so half my matches are bad, I only have to choose 17 examples for me to have a 99% chance that at least one of them was the correct one. So doing something 17 times in a computer like that, that's pretty fast. If I'm computing a homography, S is now equal to 4. Even with 50%, I only have to try 72 samples. So even though I'm totally randomly pulling these things, and I have no idea which points are right or which ones are wrong, and half the matches are wrong, with just 72 of them, I have a better than 99% likelihood that one of my sets is the correct one. And in fact, even if I'm doing a fundamental matrix, all right, looking for 8 matches, I only have to check less than 1,200 of them in order for it to be likely that one of those matches, at least one, will be a correct set of matches, so the fundamental matrix that I would get would be the correct one. One thing to notice about this table is that N does not go up very much as the percentage of outliers goes up, but it does go up pretty steeply as S gets bigger. So as the number of parameters that you need gets larger, all of a sudden the number of sample sets you have to check before you're pretty sure you'll have one that's right goes up as well. Now some of you are not table people, some of you are graph people. So what I have here is a graph where I just did S equals 4, so like a homography. And on the axis on the bottom, you can see the percentage of outliers. And you can see that the number of samples required, which goes all the way up here to, well, when I make it 0.8, it's above 2,000. But it stays low for a very long time. And that's the really cool thing about RANSAC, is that it stays low even with a relatively high percentage of outliers.